all of that. So my work, I'm a plant physiologist, and you wonder why I'm doing this. One of the great things about universities is you can follow your passions, and if you get interested in something and you're working on something interesting, you know, your administrators usually let you just keep going. So this includes meteorological analysis, which is not my background, but my whole career has been involved with using CO2 to measure metabolism of plants, and that's in closed boxes. So you really, and we've built a lot of systems to measure metabolism of plants in boxes, and sometimes those boxes start to get pretty big, and then you think, gosh, you know, we could really measure the metabolism of the whole valley with CO2, and needs all the right sensors and all the right things. And if we do the metabolism of the valley, well, we can do atmospheric mixing, and that's what led to this. Now, I want to say I might not have gone so far in this, except my colleague Larry Hipps, who is a meteorologist, has helped me a lot with the analysis of this. And Randy Martin's just walking in. Randy also has helped a lot with this. Those two guys have really inspired me to keep looking at these things. What I'm going to show you is a lot of stuff that is very counterintuitive. Now, we got a lot of climate experts here, and it may not be so counterintuitive to them, but to the public, there's some aspects of our inversions that we don't fully appreciate. This is a great picture. Andrew McAllister took it, and I kept his copyright. He's a photographer that lives here, takes a lot of interesting pictures, but I like it because it doesn't show orange air. It clears an inversion, and you know, they're not all orange air, but it clearly shows the differences. This is that big radio tower by KUSU, you know, and I guess we're right here in this picture right now. But it shows you how dramatic these inversions can be. And of course, let's see, the inversion is the fact that it's cold air settles, cold air in the bottom. So what I'm starting out with is a series of cartoon drawings about how these inversions form and somewhat how they can disappear. These are review for a lot of people, but I like cartoon drawings because everybody gets on the same page. So here's our valley. Wales, Vales, and the mountains on both sides. This is a typical day in the summer. The sun shines in the ground, warms the ground, and hot air rises, and the air mixes, and we're all fine. And this happens everywhere on the planet, just like this. Because we're at mountains, we can put weather stations up here. As you go up, the air gets cooler. So in meteorology, that's called the adiabatic lapse rate, and the dry rate is 10 degrees C per 100 meters. So typically, if the air is mixed, we get 16 degrees C cooler on the top of Mount Logan than we do here in the valley. And we see that regularly, about that gradient. What's less well appreciated is what happens at night every single day of the year. We get an inversion. The middle of July, the hottest days of the year, we get an inversion. Not quite 365 days a year because there's storms sometimes, but this is night and no radiation anymore. Cold air is more dense, it settles, so instead of getting cooler, it gets warmer, and there's an inversion. Now, because of this, we do not have to wait until bad days in January to study inversions. We had a lot of opportunities to study inversions because they set up virtually every night. Here's the part of it that gets really interesting. This is not exactly like taking a piece of glass and putting it over the valley. There's a transition zone in here. What's going on in that transition zone? How much mixing is there? It's less mixing, but it's not zero. And that amount of mixing in that transition zone makes a big difference in our air quality. And I'll tell you the overarching goal of all of this work. I'm going to show you data, the historical data of our air quality. If we can understand the mixing, we can back calculate the rate at which we're putting things into the air. Right now, we get 3 good years and EPA comes in and they give everybody high fives and they say, good work, you've cleaned it up. You know, and of course, we're sheepishly walking around because we know we didn't do almost nothing. And then we get 3 bad years and we have draconian sanctions and we still didn't do anything. It's the meteorology. You would think EPA would get that and they would give us a bunch of money to understand the meteorology. Particularly here, we have one of the most unique valleys really in the world because of this cartoon drawing, because it's not open. It's a bowl, and boy, we have unique opportunities to really understand what's going on. So, in addition to this transition zone, we also know we get mixing along these edges. This stuff heats up, and so the edges of the bowl heat up. That's the part we want to understand, and that's what's leading us to using CO2. We can measure how much we put in, how much does it build up, how much does it mix, and go out. Back to the daytime. Same slide as I showed you the first time. Now this is daytime in the summer, actually spring, summer, and fall. Now what happens this time of year? It snows, and we get snow down here. And as we all know, snow reflects the shortwave radiation from the sun, so those bars go away. The mixing is dramatically reduced when we have a layer of snow, and it reflects, bounces out, boom. Now the daytime comes and we still have an inversion because we can't heat the air and mix it. And this is the huge fundamental problem here, is the snow on the ground, because now can't heat up and mix. I'm going to show you some data about how much that snow affects air quality too, but it's huge. It's a bigger factor than we often appreciate. And this is a picture of an inversion. This isn't this valley, but it could be. It's showing how socked in it can be. This is not necessarily pollution. This is aerosols of water vapor, but bam, it's a dramatic effect. So we have a unique valley, but boy, we don't have a unique problem. This is a map of western U.S., the cold air pools. Reno, Boise, Missoula, Spokane, all of these places are mountain valleys that have persistent cold air pools. We call them inversions, but it's better to say persistent because we get inversion every night. It's the persistence of them that's really a problem. You would think EPA, federal agencies would be putting a lot of money into studying this problem because it is so prevalent over so many places. It isn't just a Utah problem. So we go to Google Earth, take a picture of the valley, and using Google Earth you can draw a transect and then get a side view of the valley. So now this is not a cartoon drawing anymore. This is a scale drawing of the mountains and the valley, and I've put our inversions on here. 100-meter deep is a shallow one, and it can be up to 400 meters deep, and this is what they look like. And the thing that's amazing about this is, wow, they're thin. They're thin layers of pools of air across the valley floor. Even though when you're in them, it seems deep, 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 but when you look at them from the side, they're thin. But it gets worse than this. This is something I started out my TED Talk with. Everything we do magnifies the heights of the mountains, so it makes stuff look more interesting. And this is no exception. Our mountains are about 1.5 kilometers above the valley floor. but it's about 15 or 20 kilometers across the valley. So even this Google Earth drawing is very inflated vertically. The mountains are maybe 5 times higher than they really are. So I redid this diagram to where the vertical axis and the horizontal axis are now equal. And it's what you get. Our mighty mountains that look so high really are, it's just an optical illusion. Now those skims of inversion layers are really thin across the valley. In fact, they're so thin that when we take our best radiometers and measure the radiation, you would say, oh my, this really blocks the radiation. We really can't even detect the inversion by the blocking of solar radiation, just because they're so thin. And that when there's really bad air the next time, look straight up. You can't tell it's an inversion if you look straight up. Of course, if you look at the Wellsvilles, you can easily tell. Or if you come into the valley from here, you can easily tell from the top down. But they're a very thin layer, all of which makes it more remarkable that our pollutants get trapped. And how well do they move sideways in this, and how well do they move up? This is what we'd like to better understand, so understand the mixing. This is such, I'd like thinking of this diagram. I should put it on billboards or something so we all understand how thin these inversion layers are. Okay, this is a hypothesis. Our air is gradually improving. Now this is data that Randy was gracious enough to send me. You can also download it from UDAC. But I took the air quality for the winter. Now winter, December 31st to March 31st. I'm going to show you a series of slides of this. 120 days. This is cumulative PM 2.5, so it's each day, if it was 10 and the next day was 20, you just add up the days of air. There's a lot of different ways you can calculate this, but this seemed like the most fair way. But the other ways give you similar answers. So here's the take-home message from this. This is a best fit regression line. Wow. Just wait. Look at this, the air is getting better, but look at the scatter in that. Each dot is 1 year, so we started in 2001, so we now have 17 numbers to work with to make this prediction. Look at the scatter. Now, if you're a scientist, you go, we got to do some work on the experimental error in our procedures because there's a lot of scatter, and the slope of this line is really important. What do you think the R squared of that line is? Everybody's used to looking at data. Not real high. 0.41. And now for a scientist, yikes, we need to do some work. But Jacob Johnson's a statistics student in the back working in our lab, and I had him crunching numbers on this stuff like crazy. Now what do you think the probability value is for this line? The probability of a significant slope, a slope different than 0. It's really probable. So assuming you fit with the linear fit, this looks pretty good that the air is going down, but it's also really noisy. And if we took these years out and we just did this, not getting better since 2006. We have some early years when it was pretty bad. In the year 2002, 2003, the university put in a new central energy plant that replaced coal, some coal, with natural gas and way more efficient. That USU's big place. We were putting a lot of stuff in the air. So some of those things in here that were happening then are not here anymore. So There's reason to think this is technological improvements that's making this, the air get better. But as scientists, Science 101, correlation is not causation. So don't tell me the air is getting better, tell me why it's getting better. Come up with the mechanism. So okay, we'd like to think technology is getting better, the air is getting cleaner. What about that snow on the ground that reflects the light and makes the inversions way more frequent? So we went, the C in our department is climate. We got the climate scientists in the front row. So working with them, we got the data for the number of days of snow cover for the last 17 years in the valley. And it's tricky because it's a human observer and they say, is there snow or not? And I think they put the number of inches or something down, but 1 inch. So if it's covered with snow, so we added these days up for each winter, and then we got the 3 stations that record that, and they were all pretty similar, but we averaged them, and that allowed us to calculate the statistical effect of snow cover on air quality. Here's that same parameter, cumulative PM2.5. It's micrograms. This is micrograms for PM2.5 over 120 days. So they all get added up. Well, snow cover reduces the air quality. We know the mechanism for that. So how much then of the downward slope of air quality is due to changes in snow cover in the valley? This year, we don't have a lot of snow cover, and we've had terrifically good clean air this year. At least the last several weeks been good. That's a few weeks out of 17 years of data. I thought the snow cover would be getting less. If we have global warming, slight increases in temperature, melt the snow. If there's less snow, there's less inversions, less air. There's no long-term trend. Here's the same period, 17 years. Days of snow cover, there's no relationship. We're not getting less snow, statistically. Even though it's really noisy, 40 to 120 days each year of snow. What this means is snow cover is unlikely to be affecting our downward slope of our air quality. So now we make an index, air quality divided by days of snow cover. So we can test that hypothesis, and that's what this next graph is. Here's the same graph adjusted for snow cover. It's that cumulative PM2.5 divided by days of snow cover. Still slopes down, but the slope is less. R squared's less, the probability is less once we adjust for days of snow cover. And up here is the original graph, not adjusted. And you could, by comparing it like this, you can see the effect of snow cover on the slope of this line. This one has less slope, but a bit less noise, because one of the factors that affects us is snow. Now, we're not, short of going out and shoveling the snow off the whole valley, we're not controlling snow cover. So this is a better predictor of, I think, of what the air quality is doing. And it still slopes down, and it's still statistically significant. But now in the world of statistics, and we're all trained at manipulating our graphs to make whatever point we really want to make, let me take this exact same data and graph it with a little bit different x-axis. And look what happens to that data. Oop, I had to go there. Boom! There's our 17 years of data, but we graph it like this so we can predict the future. And this is, you gotta be careful who gets this, because, you know, that's one of the things we do in statistics is don't go off the end of your data. But we do it all the time because we want to predict the future. So you can see why I put this graph in here. Wow, just wait till 2050 when we have great air, clean. The data proves it. Yeah, right, and they could just as well fit this with the line that looks like that too. It's not enough data to be really confident. That's why each year's data is really, really interesting. And that's why if we understood the meteorology better, we could reduce some of that experimental error, just in the way we did here by correcting for the effect of snow cover. Okay, now let's look at the valley. Here's that Google Earth, the beautiful images. I kept Bear Lake in here, get perspective. Our nice valley. This disk right here is a CO2 emissions hotspot. We know that. The cars are here, the people are here, CO2 is being produced here. Now we got that thin layer of air. How well is that CO2 moving horizontally all over the valley? And can we tell how much of it's moving up, out of the valley? When I was looking at this, and these diagrams, you know how we say we live in a fishbowl and we live in a bathtub and all that, that's all great. Once you do that analysis of height and width, we ought to be saying we live in a saucer. It's more like a skim-thin saucer. And now we're trying to keep this pool of dirty air in the bottom of the saucer. We are not the only people to use CO2 to analyze atmospheric mixing. Here's the United States. I showed this parts of this talk in Amsterdam last fall, and amazing that some of those people didn't know where Cache Valley was, so we had to show them. So there we are, and we warrant our little tiny orange speck up there. This is a model of where the CO2, not a measurements, but a model of CO2. And, as many of you know, we are now actively engaged in this CO2 monitoring on a global scale. This is off the internet. If I was smarter, I'd have this play real time, but this thing moves on the internet, and you can watch winter and summer, and here's China over here, and India, and United States, and dark red's more CO2. Where does it go? How much are we producing? How does it blow away? Mauna Loa, you know, it was strategically put in the middle of the ocean so it wasn't subject to short-term perturbations. Mauna Loa, Hawaii, some people, that's where we've had the longest term record of CO2. Very, very precise. It's a great story. I don't know if there's a book's written about that yet or not, but it's a tremendous history of doing CO2. And then, of course, this flips, winter and summer. But here's the data for the last similar years. The average is going steadily up. Winter, it goes way up, and our noble plants and all the photosynthesis suck it down in the summer. If we could have continuous summer, we wouldn't have a problem. Winter comes and up and down. So these are monthly averages, and we analyze these really closely to see how we're doing on what we put in and what accumulates. And there's tiny little changes here. Here's a key point. The whole range of this graph is 15 parts per million because it's diluted by the whole planet Earth. Now imagine our saucer in the valley with our little skin sieve of air. I'm going to show you data that we jump up more than 100 parts per million day to night and winter to summer in our valley. You have way bigger changes in CO2 than this. To give you a sense of how much that's analyzed, here's 1 year of data. This is 2013. Daily numbers, weekly averages, monthly averages. The winds make this go up and down, but the point is we're using this a lot to analyze climate on the Earth. One key part of this graph, we all are familiar with parts per million CO2. That unit is numerically identical to a micromole of CO2 per mole of air. That's called the mole fraction. And the reason this is important, they're just the same thing. ppm is just a shorthand for that. The micromoles of CO2, the numerator is how much we're putting in. The moles of air is in the denominator is the volume of air in our valley. And that changes with the depth of the inversion. So we get changes in the numerator and denominator, which we can measure those precisely and see what's going on. All right, let's look at the valley in detail. You would think the airport, that's the bottom of the valley, right? That's way down there. This is the valley with colored contour lines around it. And when we draw some approximate circles, 1340 meters is the wetlands. The water flows to the bottom. And in the middle of that, now we've got a weather station. We call it the Benson Marina because it's right next to the Benson Marina. It's the lowest point in the valley. So I'm going to show you a series of pictures now of the weather stations we've set up in the valley. This is just in the last, most of these are in the last year. This is a picture of the Benson station. LAK is at the top, adjusting the antenna because we're trying to wireless transmitted real time. But it's a 10-meter tower with temperature, but the measurements are taken at the top, at the Benson Marina. The next level up is the airport, and I call this Campbell Scientific Apogee because the weather stations are here, but that's 26 meters higher than the Benson Marina. Wow, so already the airport's not the bottom of the valley, not even close, and we have a weather station there. I'll show you a picture of that in a minute. These are unique weather stations. I'll show you what's in them. The next level up is starting to get stratospheric, 47 meters up. That's downtown Logan. That's surprisingly, 21 meters above the airport, downtown Logan. These are really interesting when you calculate the volume of air because of this saucer effect. And there's our campus station. There's a little picture taken from the roof. You can see the station in the middle. That one's been up there the longest. That's about 10 years. That was where we pioneered the use of this special instrument for CO2. It was on campus. And the fifth station, strategically located on Crow Mountain, and here's a picture. If you walk out there by the spectrum and look straight north, there's Crow Mountain, 400 meters above the valley floor. That's a really nice place because that's the very top of Inversions. Now we still use Mount Logan as a reference, but Crow Mountain is, we have more instruments there. We have CO2 up there now. It's a nice reference so we can see these vertical changes in temperature and CO2 and wind. So that's the network we're talking about. Here's Apogee Instruments' backyard. And this is the kind of picture you don't want to show other people because they all want to move up here. But this was in the fall. There's our airport right there. Here's the tower, an example of the tower. And now I want to talk about the instruments. Now, this project at another place might not, what comes together in our valley after we get the unique valley, how many of those other valleys have a world-class university in them that studies climate and weather? Not many. How many of them have a suite of instrument companies making instruments for this? None. That there are more people working for environmental instrument companies in Cache Valley on a per capita basis than anywhere in the world. We're our Silicon Valley for environmental instruments. All of this is funded by those instrument companies. They've donated either the money or the instruments to do this because they're super interested in the air quality. So there's 3 unique measurements that we're making. And let's zoom in. There's the top. These are not a Davis home instrument station like shown here. There's a reason for that. When the weather's bad, we get big frosts, and the instruments have to be heated to get good data. There's a typical from rime frost. This was easy to make the measurements in the summer, but it's much harder to make all these measurements in the winter. So let's look at these measurements. Here's the tower. Most weather stations have a cup anemometer. We're all familiar with those. Those freeze up in the winter. The grease gets viscous. They're very inaccurate in the winter. So we use a sonic, a two-dimensional sonic to speed of sound, and that, especially in our low wind speeds during inversions, this is the only instrument that can measure that. The cups read 0, and it's not 0. The wind is still moving around, and I'll show you how much it's moving around, but that's a unique instrument. Fan aspirated temperature. Mostly we use those little white plates like this turned upside down, and we're measuring temperature. Those things have a slow response time, and when you get any turbulence, they average it out. If you put your sensors with the fan, it's fast response. You can see the temperature turbulence. So this instrument is designed and manufactured in Cache Valley, so it's perfect for this. And then finally, the CO2 sensor is inside of this, but this is our tracer gas. This is made by Vaisala, Apogee, and Gill Instruments makes that. And all of those companies have given us either free or discounted prices on their instruments, because we said, wouldn't you like to be part of this cool research? And that helps. And we can tell them how well their instruments work in these conditions. Let's look at temperature. Now, this is a typical graph, this shallow inversion. This was last fall. This is temperature in Celsius. It's not in the middle of the winter. Goes up in the day, down at night, not so much at the top of Logan Peak. Campus downtown, Apogee at the different elevations. Here's a shallow inversion. It's colder at Apogee than downtown, and that you think that's what, 3 or 4 degrees different there? And then campus is warmer yet. And then finally, the cold up here. Campus is a pretty smooth line because of canyon winds. It mixes the air smooth. These jagged lines indicate turbulence, cold air, warm air mixing, going up and down. But what I really want to point out on this slide is these were adjacent to each other. The red line is one of those, a static multi-plate shield, which gives us a fine average, but it doesn't indicate that turbulence. This is what those things look like, one of those multi-plate shields. They also are always wrong in the middle of the day. God, there's a whole bunch of models and stuff we do by maximum daily temperature. All of it's measured by stuff like this, and it's wrong by 1 to 2 degrees C. Like, not just a little wrong, it's way wrong. So we got a lot of errors in the climate record, but we got to be backwards compatible and try and fix them. That's temperature. Here's CO2. This was, oh, here it is, November. That ended right around Thanksgiving. This is all real time on the internet. This is some interesting data. First of all, look at the scale. 400 to 550, so this is not Mauna Loa anymore. This is 150 ppm changes in CO2, and this is not instrument noise. The instruments are accurate. The noise here is turbulence. It's CO2 going up and down because the air is mixing. Here, these dotted lines are midnight, so let's take right here. Midnight, here's the day. The air was mixing in the day. All the numbers came close to each other in the day. And then we take the following night, and it builds up. This gray one is downtown, Logan. But the downtown Logan air moves out toward the airport to Apogee, and both of those go way high. But the campus is low because we got a little bit of canyon wind, so we're clean. And look at Crow Mountain, clean all the time, except when these things, when the air mixes, Crow Mountain get a little blip. All this CO2 laden air blows to the top of Crow Mountain and spikes it, just a little bit. But this is common. Here's a good example. This is common every night. CO2 builds up downtown, cold night, build up. Then in the morning, the canyon winds stop, and we get a little puff of air from downtown. Boom, it spikes campus every day in the morning. You see a big spike on campus. It's because the air shifted and blew all the CO2 up to campus. That's the kind of data we get, which is both shows mixing and cycling. And when this gets high, that means inversion and trapped air. A lot of trapped air. This is a little bit more complicated, but this is our worst air episode this year. I think it's the worst. It's early, after Christmas, early January, the 3rd to the 7th of January. So here's the UDAC graph of PM 2.5. And it built up. We got to, in the 40s, and then it started to come back down. Here's temperatures during those times. And you can see these dips are big inversions. Now look at the daytime. It warms up in the day, but it's still an inversion. Doesn't warm up to clear the air, because the dark green line is the top of Mount Logan. The light blue line is Crow Mountain. Now look at what happens here. Warming up, starting to go away. Now this is the difference. Still an inversion. We got a little warmer here. And this is starting to go down. And finally, we have a lot warmer here, and the air started to turn over, and the PM 2.5 goes down. I mean, that's pretty straightforward stuff, but it shows you how the PM 2.5 builds up when there's no mixing and then blows up. And sometimes this is dramatic. Now, Randy could probably tell us afterward what's going on here, because there's some erratic, this is a hard thing to measure, and there's some spikes in this data that I don't think they're real. That's all right. We're more interested in this part anyway. So there's mixing in PM 2.5. We've done a lot of work on horizontal mixing. How is it that the air can move horizontally under this skiff of inverted air, but very little vertically? This is a typical night. This happens to be November. There's the wind speed, and the arrows on that show the direction of the wind. So what's going on is we get a puff of wind, and it might last for 30, 40 minutes, but it's all from the same direction. So it pushes the air over here, and then it changes, and it pushes it in another direction. Here's the key to this for the colors of light. So the air isn't really jiggling. It's more wandering back and forth. And from this data, we can make a graph like this. So here's the airport. This particular graph starts with, here's the instrument companies, and here's a molecule of air moving around at night. And when I think about the speed of the air movement and the direction, the thing that I think of is it's like a drunk. It's going about this fast, but it's no particular, he's just wandering around. And by 8 a.m. the next morning, he ended up out here by Benson somewhere after traveling. That's what the air is doing at night, helping to horizontally mix the pollutants. Now, I got two other slides that show you different nights. That's the wind run, that was Thanksgiving Day, that night. Here's the next night, same starting place, a similar pattern, walked around here. Now some nights goes in one direction. Here's the next night, started here at the instrument companies, and it ended up in Smithfield. But that's a lot of horizontal movement underneath these. How much vertical movement was there? That's many kilometers of horizontal air movement caused by tiny, tiny changes in the density of the air that's pushing this air around. And we know it mixes because of the CO2. We get the CO2 sourced in downtown, and CO2 spreads out pretty fast in the valley. If you're used to looking at these, you understand them. I put them in here because they're interesting. It's a lot of data. We could spend a lot of time in this graph. These are called the wind rows. And 360 degrees, so that this shows the direction, and the color shows the speed. Now, this was right now. I downloaded this maybe 40 minutes ago. So it's the last 24 hours, and it's pretty windy right now. These are fast speeds. But here's the point I want to make, that by studying these, you see the directions of wind. Look at our valley right now. The downtown, there's wind coming from the south, and Crow Mountain, it's coming from the north. And then you go over here to Benson, it's coming from the northwest. And Apogee and the campus rooftop, it's coming from the south. Man, we get stations all over, and the air is, it's just amazing. It tells you that there's a lot of mixing, horizontal mixing going on, at least now. This is a clean air and a little more clear. When it's an inversion, all these lower ones go red. And there's even a white, which is calm. This is tiny, red is tiny air movements. It's not zero, it's just tiny, and they tend to randomly move all over. All right. Now let's look at some data for the last couple of years. This is from our longest record for here that is from the University of Utah has a network of these stations in Salt Lake, and they have one here in Cache Valley that they've run for a while. This is a real high quality station. It's inside, they have an inlet from outside. And this is 30 summer days, last summer. Look at the change of CO2. This is summer. The days go way up in the summer, and the nights rather go way up, and the days come back down to ambient. Every day is mixed, but the nights go way up. Wow, let's look at summer for the inputs and outputs of CO2. This is some of our data. The take-home day, it all blows out together, builds up at night. This is typical, 10 parts per million per hour of CO2 buildup at night. Now we have our box. We'll calculate the size of the box and the measured rate of CO2 increase, and let's calculate where that CO2 is coming from. In the summer, no home heating. Here's the volume of air. Here it is again. This is a series of, I left all my calculations on here because you can pause the seminar and see them. Shallow inversion, 50 meters deep. There's 17.5 times 10 to the 11 moles of air. That's an easy math to do, volume of air. Take that number, 17.5, and it's going up 10 an hour. We have 17,500 kilomoles. This is, all these are a bunch of slides in kilomoles of CO2 now, per hour. That's appearing in our air. Where's that CO2 coming from? In the summer. A lot of people driving around at night in the summer. There's the same number, measured rate of input. This is vehicles at night. Now, we are not Manhattan. People don't drive around at night around here. It's quiet. And I took a real high rate. Cars now get 10 moles of CO2 per mile. That's an efficient car. 3,000 cars, all these are high numbers, 600. That CO2 buildup is not caused by cars, so I had to pause here and say, But I have this background in plant physiology. We are an agricultural valley, and there's a lot more plants in this valley than people, and especially in the summer. They take CO2 out of the air in the day, they put CO2 into the air at night, so I did the math, 50% covered by plants, boom, 18,000, and now you do some addition. There's a view. That's why we got a lot of plants. So we can easily account for all the CO2 at night in the summer. 18,000 in, 17,000 appearing. Those numbers are close. You think, okay, we're on to something here. We got inputs and outputs, and they match for our closed box. Now let's do the winter. This is per hour. The winter we have persistent cold air pools, so we're going to do per day for a 24-hour day. Here's 6 months. Summer, respiration. You get into the fall, and the plants should be frozen and less CO2. It's still fluctuating. Here's our inversions where the CO2 gets persistent and hangs around, and we get a lot of CO2 buildup. That's associated with PM 2.5 as well. So now take a closer look, zoom in on January. This is January 2017, and here's our inversions. We had some periods of clearing and CO2 buildup. Here's the take-home message from this. When these numbers go down, that means there's atmospheric mixing and the valley is partially getting flushed. During these worst persistent inversions, here's one day, boom, down at night. That means the air is going somewhere. That CO2 is not sticky, it's not being absorbed. Goes up the next night, down. There's a lot of fluctuation in the day for CO2, suggesting that there's more atmospheric mixing than we usually think. So let's look at the inputs of CO2 in the valley. This is the coldest days of the year. Now, I want to thank Randy for saying maybe Questar Gas Dominion Energy has that data. And after it took me about 25 phone calls, and I finally got to the guy that sits in a chair and watches the meter, and oh, sure, I have that data. I said, what's your peak? How cold does it get? 80, this is decatherms a day, 80,000 decatherms a day. And you do the math, 96,000 kilomoles a day. Now this natural gas, it's not stored, it's getting burned. That's the input of CO2. I learned something else about this. This is just fascinating. The gas just shows up right at your house, kind of like the electricity. There's a huge 12-inch line at, what did he say, 800 PSI coming in from Kemerer, Wyoming, that they put in 2002, I think. And there's a loop in the valley. This is the old line coming in from Ogden. That's how we get our natural gas. It's a big loop in the valley supplied by two directions. So now we know all that burned, that we know the CO2 showing up in the valley. Here's the rest of it. Amazingly enough, only about half of that's our homes. About roughly half is commercial for the CO2 input. This is our central energy plant at campus, which we do electric cogeneration here. We're big for CO2 users. But Gosner Cheese uses gas to process cheese. Pepperidge Farm, there's a lot of commercial users. But there's the total. Look at how that dwarfs the vehicles. This is a day now. So it's not just night driving, it's day driving. Data from UDAC. This is a staggering number. As small as this seems, Randy, how many registered cars are there in Cache Valley? I mean, 80,000? That's like all the cars are driven 25 miles a day. And then here's our 10 moles a mile. So this is a pretty high estimate. Now here's the people. I had to put us in there. We're teeny. So you add it up, 118,000 kilomoles a day. Here is volume of air. Now the top is the CO2 input. The denominator is the volume of air. 39 times 10 to the 11th, do the math. 30 ppm per day buildup of CO2 on the cold days of the winter. That's not a big buildup of CO2. So Mark Blomqvist reminded me that respiration, microbial respiration under the snow in the winter is not zero. There's microbes still respiring. The ground's not frozen. This comes from a couple of papers. It's a high estimate. So maybe 9 from the microbes. Add those two numbers together. 39 ppm a day from all the sources in our air. And now I'm going to do an overlay here. Here's our measured numbers. These are going up way more. Let's round this to 40. They're growing up way more than 40 at night. And then they come back down in the day. I don't understand why what's going on. We're not putting enough CO2 in the air to account for these changes. The instruments are corrected for temperature and pressure, especially these instruments from the University of Utah. So we have things going on with CO2 that we don't yet understand. But the point of this is I think we can get there. I think with monitoring CO2 and calculating these kinds of mass balances, we can see how well our air is mixed, see how much that leaves. And the final goal is by doing that, we can then back calculate the rate at which we're putting pollutants into the air. And we can get past those days of big congratulations for fixing the problem and then draconian sanctions for screwing it up again. We can calculate the rate at which we're putting stuff in the air, particularly for our valley, just because of the unique topography of the valley. And there's my last slide, back to that. But I'm going to leave this one up here a second because this is the biggest puzzling slide with the calculated CO2 increase and then the measured result. And even this is with the, we only get this high with the shallow inversion too. If the inversion is deep, stuff has more room to disperse and the CO2 doesn't build up as fast. Our worst inversions are the shallow inversions because we're really trapped in a small volume. And I think it's a reasonable hypothesis to say shallow inversions are also associated with less atmospheric mixing. On the days when the inversions are deep, we see Crow Mountain kind of starting to get high in CO2, and then the CO2 is leaving the valley after that. So this is where we're at, and where we hope to go with this. We're going to need this complicated stuff. We're going to need meteorologists and climatologists and a lot of people helping to work in this. But the payoff is huge if we understand our airshed mixing. And I see a time when this university and the instrument companies are coupled to do stuff that's, the whole world wants to know this. I mean, there are thousands of mountain valleys in the world. Not all of them have bad air, but most do, and they all have inversions. So whatever we find out here is relevant to lots of mountain valleys. So I'm going to stop here, and I'd be happy to take questions.